So it's a Saturday afternoon, and we all know what you're really doing. However, we all know what we would actually like to be doing, and that is figuring out the overall polarity of certain compounds when there's more than one bond taking place. That's right, using VSEPR we can actually determine whether something is overall polar or overall non-polar. And there are a couple of steps in order to do this. Stay tuned, this video will address that. So, when it comes to the overall polarity of compounds, what we have to understand is that bonds are vectors. So this is a physics term describing a quantity that has a magnitude or a value and a direction. And the significance of the directions is that, your bonds based on their directions, okay, so I'm going to write based on arrows, right? So directions, whether it's this, etc., okay, can cancel each other out. And so sometimes you will have an overall magnitude of 0, but not because there's no bonds being enacted on the center atom, but because the bonds cancel each other out. So what does that mean exactly? So for example, let's say we have the compound CO2, where we'd have carbon in the middle, least electronegative atom, just like we did with our Lewis dot diagrams. And you have an oxygen on each side. Now, oxygen has a bond or an electronegativity value of 3.4. Carbon has about 2.6. And then again, 3.4. Well, when I draw the diagrams, I would see that, yes, I would have a bond dipole towards the oxygen, making it partial negative, and I would have that on both sides, right? Because there's an oxygen on each side. And the overall dipole on the carbon would be a positive because it would unevenly share its electrons with oxygen. Now, bond dipoles, right? The directions here, because we have, you could say, a value of 0.8 going this way, and then another value of 0.8 going this way, these bond dipoles would cancel each other out because they're in opposite directions. And so ultimately, there would be no resulting dipole. And that's because, your directions cancel out. So we're going to write directions cancel out. Now, why is that significant when it comes to the overall polarity of compounds? And so, really, we think about polar molecules in regards to their overall symmetry. And the first thing that we have to recognize is that polar molecules are asymmetrical, or that they're not symmetrical. And what that means is that they're in different general directions with regards to the center atom. And so while we anticipate different directions for a polar molecule, a non-polar molecule is going to be symmetrical. And that means that it has the same general direction with reference to the center atom. Now, how does that actually look if we're examining a molecule or a compound? Well, let's say we're comparing two molecules. You have methane, and then you got chloromethane here, okay, CH3Cl. Well, when I draw the VSEPR diagrams, just a quick reminder here, these hashed lines are the same as the dashed lines that we would have seen us draw earlier. So whether you're using hatched lines or dashed lines, they both mean the same thing. So let's say I assign electronegativity values on each of these. And again, these values are going to be from the periodic table. Now let me just quickly write in the electronegativities of the carbons. So when I draw my bond dipoles, if I look at the first diagram of methane, I know that because carbon has a higher electronegativity, the bond dipole will face towards the carbon, and that'll be from all the hydrogen bonds. Okay. Now, same thing is true with the other one, where the hydrogens will face the carbon because of the higher electronegativity. But then I'm going to draw this in another color here. Then the chlorine will actually pull on the carbon away. Now, in the first molecule, I see that all the bonds point towards center, right, which is the C. That means that they're in the same general direction. Okay, now what that more specifically means is that if they're in the same general direction, this is a symmetrical compound. Now, it's not about them being towards or away, but it's all about them being all towards or all away. Now, when I look at this one, the 3 hydrogens are towards, but then the chlorine is away from the center, right? And we're going to write from center. What that means is that this is not symmetrical because they're not in the same general direction. Okay? And again, it's not about being towards or away. It's about being all towards or all away. So, if this is symmetrical, then using the theory we outlined before, this would be a non-polar compound. And if this is not symmetrical, this would be a polar compound. So the methods for determining overall compound polarity would be first to draw the VSEPR diagrams. Then once we have the diagrams, we're going to draw all the bond dipoles, of course, with reference to the center atom. That's where all the bonds are happening. And then third, we're going to assess symmetry. And if the compound is overall symmetrical, it's going to be nonpolar. And if it's asymmetrical or not symmetrical, it's going to be polar. Now, some people might ask, well, why do I have to draw the VSEPR diagrams at the beginning? Because couldn't I do steps 2 and 3 without drawing VSEPR? Not always. And that's because there are certain shapes that are automatically going to be asymmetrical because of their natural geometry. When we say the word symmetrical, remember what we mean is that it can be folded into 2 equal halves, and not every shape can do that. So when it comes to symmetry, we're going to first look at the VSEPR diagrams. Okay? And that is going to be important because if your VSEPR diagram has any bent, or sometimes called angular, or as well trigonal, okay, bipyramidal, oops, then we're going to say that these, okay, are automatically polar. And we don't have to look and see, are they all towards, all the way? These are automatically asymmetrical shapes. Okay, so they're going to automatically be polar. And so just reminder that your bent would look something like this with 2 lode pairs, right? Or the angular. And then the trigonal pyramidal looks something like this, right? Where I'd have my hatched lines here, and there's a lone pair over here. So any of these 2 shapes are going to automatically be polar. But if you don't have one of these 2 shapes, then you're going to assess the symmetry just like we did over here. We're drawing the bond dipoles, seeing if the vectors are generally in the same direction or are not all in the same direction.